This presentation is delivered by the Stanford Center for Professional Development.
How are we doing? Spring apparently is here. Just like California. One day it's winter and one day it's spring. Hopefully it's here to stay. So we had talked about doing it. We did this last time. We did an unsorted vector implementation of the map that just did a little struct of the key value pair. And then we went through that both add and get value, right, are running in linear time in that form because of the need to search. Search to find a value to overwrite it, and search to find a value to pull out the existing match to it. And that if we went to the sorted form of that, right, we could get value to capitalize on that binary search property and be able to quickly find the key if it exists in there, or to determine it doesn't exist. But that add then still suffered from the shuffling problem of we can quickly use a binary search to find where the new element would need to go, but if it doesn't already go there, it doesn't already exist, we're going to have to shuffle to make that space. So we have still a linear factor in there that we're working on getting rid of. And then I noted at the bottom that neither of them has any built-in overhead per element. There may be some capacity, excess capacity in the vector that we're absorbing there, but there's no 4, 10, 8 bytes, some other chunk that every element is taking as a cost. So we started to talk about this at the end on Friday, and we're going to go with this and see where this takes us, right? We had the idea of the vector, and we know what vectors' constraints are, right? This idea of the contiguous memory, and we were going to think about the linked list for a second to see if it was going to bias anything, right? That it tends to have an inverse relationship, that once you know where you want to insert something, it's easy, right, to do that rearrangement, because it's just a little bit of pointer rewiring that needs to happen in that situation. But it's hard to find the position to insert. That even if the linked list is in sorted order, right, knowing where the S's are, or the B's are, or the M's are, right, it's still a matter of starting from the beginning, that your only access in the ordinary singly linked list, right, is to start at the beginning and work your way down. And so I'm going to kind of take you through a little bit of a thought exercise about, well, what if we try to do something about that? That right now, having a pointer coming into bashful and then the subsequent ones going in sorted order isn't really very helpful. But if we were willing to kind of try to rearrange our pointers to give us the kind of access that we have in the sorted array form. For example, if I had a pointer to the middlemost element, in this case the grumpy that's midway down the list, if I had that pointer, and from there, right, I could say, well, is the element I'm looking for ahead of grumpy or behind grumpy? So having grumpy split my input in half, if I had that, right, then that would actually kind of get me sort of moving toward that direction I wanted to get, which is using the binary search property to kind of facilitate throwing away half the data and look into just the half remaining that's interesting. Well, if I had a pointer to grumpy, that doesn't quite solve my problem, right? As a pointer to grumpy could get me kind of halfway down the list, but then the pointer's coming in this way. If I inverted the pointers leading away from it, right, that's also kind of helping to facilitate what I'm trying to do, so I could point to the middle and then kind of move away. And then if I actually just applied this same strategy, not just at the topmost level, but at kind of every subsequent division down, from the half to the quarter to the eighth to the 16th, that instead of having a pointer to the front of the list, if what I really maintained was a pointer to the middlemost element, and then that element maintained pointers to the middle of the upper quarter and the middle of the lower quarter and all the way down, that I could pull up this list into something we call a binary search tree. So that the way I would be storing this, right, is having a pointer to a node, which is expected to be the median or middle or somewhere, right around the middle of the values I'm being stored, and that it has two pointers, not just a next or previous or something like that, that are related to all the elements that precede this one in the ordering, and all the elements that follow it are in these two pointers. They call these subtrees, coming off the two smaller trees over here with 3 elements on this side and 3 elements on that side. And that each of those nodes has recursively the same formulation, right, that it has 2 subtrees hanging off of it that contain, given any particular node, that there is this binary search ordering here that says everything that's in that left subtree precedes this node in the ordering, and everything in that right subtree follows it. And that's true for every node throughout the entire arrangement here. So this is called a tree. And this particular form is actually called the binary search tree. I'm going to throw a little bit of vocabulary at you because I'm going to start using these words, and I just want to get them out there early so that you understand what those words mean when I start using them. Is that each of the cells in here, like the cells that are allocated for a linked list are individually heap allocated, that we're going to have pointers that allow us to get back to them. We typically call those nodes in terms of tree. Often I'll call it a cell or a node in the list kind of interchangeably, but I'm more likely to use a node when I'm talking about tree. And that a tree is really just a pointer to a node. The empty tree would be a pointer whose value is null, so pointing to nothing. A singleton tree would be a pointer to a single node who has left and right subtrees that are both empty or both null. So bashful by itself is a singleton tree, a pointer into bashful. When we talk about subtrees, just means kind of, looking at the top, Grumpy has two subtrees, it's left and at right, that themselves are just smaller forms of the same recursive structure. And then we would say that Grumpy is the parent of Doc and Sleepy. So those are the two children nodes, and as we'll call them, the left child, the right child. And the node that's at the very top, the one that our external pointer is coming into and then kind of leads away, is called the root node. The first node of the tree where we first start our work is going to be called the root. And these nodes down here at the bottom that have empty subtrees are called leaf nodes. So a node that has no further subtrees, so by itself has empty or null left and right trees, is called a leaf. So that actually means the tree is kind of upside down if you look at it, right? The idea that Grumpy's the root and these things are the leaves kind of shows you that most computer scientists apparently don't get out very much because they have not noticed that trees actually grow the other direction. But just kind of go with it. You'll be speaking tree speak in no time. So any questions about kind of what we got basically set up here? So there is a whole family of things that come under the heading of tree in computer science. We're going to look in particular at this one embodiment, the binary search tree. But before I get deep down in the details of that, I just want to back up for a second and just talk about what trees in general mean and what kind of things are represented and manipulated as trees, so that you have a sense of the broad notion of tree as a computer scientist would see it. Is just that a tree is a recursive branching structure where there are nodes which have pointers to subtrees. There may be one of those subtrees, there may be 10 of those subtrees, there may be 2, depending on kind of the nature of the tree we're working at. There may be a constraint on exactly how many children they have, or some flexibility in the number of children they have, depending on what's being modeled here. There's always a single root node. There is a node that kind of sits at the top of this hierarchy that leads down to these things, and that to form a tree there has to be a reachable path from the root to every single node. So there aren't some nodes that exist way out here, and there aren't 2 different ways to get to the same node in a tree. That if the midterm is kept in the folder called exams, which is in the folder called CS106, which is in my home folder, right, there's not some other way that you can get to the midterm. The midterm lives exactly that part in the tree, and there's no circularity or loops in the structures. And so a lot of things do get modeled trees. The one I drawn here is just the file system, right? You think about how your files are maintained on a computer. There tends to be a structure of an outermost folder, which has inner folders, which have inner folders. And along the way, there's these files, which you can think of as leaf nodes, right, that have no further subtrees underneath them. And that you can talk about what is the size of, let's say, all of the files in my home directory. Well, it would be kind of recursively defined as kind of summing over all the folders within it, how much storage is being used by those, which when it gets down to a leaf node can say, well, how much space does this file take up, and kind of add those together. Things like your family trees, right, sort of modeling genealogy. Things like the decomposition tree in your program, right, main calling, read file, calling setup boggleboard, calling give instructions, right, that there's a tree structure to that about what pieces use what pieces and descendants from there. The ones we're going to look at in particular are in the family of the binary trees. So a binary tree has 2 children, exactly 2 children. There's a left and a right pointer coming out of each node. One or both of those can be null, but there will never be more than 2 children, right? And there's sort of space for recording 2 children, as opposed to things that are ternary, which have 3 possibilities for children, or n-ary, where there may be some, 4 or 8 or some other number there. And in particular, it's the search tree that is going to help us get the work done we want here, which is there's not just any old arrangement of what's on the left and the right side, that the nodes are going to be organized in here to facilitate binary search by keeping 1/2 over on the left and 1/2 over on the right, and that we will know which half something goes in by virtue of looking at the key. So let's take a look at a simple example of a binary search tree with numbers. So if I have a struct node that keeps track of an integer value and has 2 pointers, the left and the right, that point away from it. And in this case, my root node is 57. And looking at 57, I can tell you that every value in this tree that is less than 57 will be in the left subtree. There will be no values that are 56 or lower on the right side. And that will be true at every step down the tree. So if I'm looking for something, that actually gives me that immediate access we were using the vectors sorted property for, which is if I'm looking for the number 70 and I start at the root node of 57, then I know it's not in the left subtree. So assuming that about half the nodes are pointed to over on that side, I've now discarded half of the input even from consideration. Well, I start at the 70 and I say, okay, well, if 57, I say, okay, well, it must be over here. Then I, again, recursively apply the same search property here. It's like, well, if I'm looking for 70, is it going to be before or after 79? It's going to be before. So in fact, I throw away anything that leads away on the right subtree of 79 and work my way one level down. So each step in the recursive search is represented by kind of taking a step down in that search tree, working my way from the root down to the leaf nodes. And I either will find the value I'm looking for along the way, or I will fall off the bottom of that tree when I haven't been able to find it, and that will tell me, oh, it couldn't have been in the tree, because the only place it could have been is the one that followed the binary search property. And so if I look for 70, I say, well, is it greater or less than 62? It's greater. Is it less than or greater than 71? It's less than. And then when I work off there, I get to the empty tree. I say, well, if there was a 70, that's where it was going to be, and it wasn't there, so there must not be a 70 in this tree. So it is exactly designed to support one kind of search and one kind of search only, right, which is this efficient kind of divide and conquer binary search, work its way down. The other kind of things, let's say, that trees are used for may not need this kind of support, and so they may not go out of their way to do this, but the one we're actually very interested in is because of maps doing a lot of additions into a sorted facility and searches in that sort of facility. If we can model it as a binary search tree, we're able to get the best of both worlds, to have that super fast logarithmic search as well as have the flexibility of the pointer-based structure to help us do an insert. So if I'm ready to put a 70 into this tree, that the same path that led me to where it should be tells us where to put that new node in place. And if all I need to do to wire a node in place is kind of create a new node in the heap and put the pointers coming in and out of it the way I would in a linked list, then I should be able to do both searches and inserts in time proportional to the height of the tree, which for a relatively balanced tree would be logarithmic. So sounds like we can get everything we've wanted here with a little bit of work. So let me tell you, just to do a little bit of playing with trees, just to kind of get used to thinking about how we do stuff on them, and then I'm going to go forward with implementing map using a binary search tree. Trees are very, very recursive. So for those of you who still feel like recursion is a little bit hazy, this is another great area to kind of just strengthen, right, your thinking about recursive. And in fact, I think a lot of people find operating on trees very, very natural. Because trees are so recursive, the idea that you write recursive algorithms to them is almost like you do it without even thinking, right? You don't have to think hard. You're like, you typically need to do something to your current node and then recursively operate on your left and your right. And it's so natural that you don't even have to stop and think hard about what that means. And so your base case tends to be getting to an empty tree, so having a pointer that points to null. And in the other cases, have some node operate on your children. Some of the simplest things are just traversals. If I have a tree structure and I'd like to do something to every node, go through it and print them all, go through it and write them to a file, go through and add them all up to determine the average score, any of these things, right? I'm going to need to do some processing that visits every node of the tree once and exactly once. And recursion is exactly the way to do that. And there's a little bit of some choices in when you're handling a particular part of the tree. Are you handling the current node and then recurring on the left and right subtrees? Are you recurring first and then handling the nodes? So some of those things we saw in terms of the linked list that change the order of the processing, but they don't change whether you visit everybody. It's just a matter of which one you want to do before. I'm going to look at a couple of the simple traversals here, and I'll kind of point out why that mattered. If we look at in order, so what's considered an in order traversal is for you to operate on your left subtree recursively, handle the current node right here, and then operate on your right subtree recursively. The base case, which is kind of hidden in here, is if t is null, if we get to an empty subtree, we don't do anything. So only in the non-empty case are we actually processing and making recursive calls. So if I start with my node 57 here being the root of that tree, and I say print that tree starting from the root, it will print everything out of the left subtree, then print the 57, and then print everything out of the right subtree. And given that gets applied everywhere down, that the effect will be, well, 57 says first print my left subtree, and 32 says, oh, well, first print my left subtree, and 15 says, well, first print my left subtree, and then 7 says first print my left subtree. Well, that one's empty, and so nothing gets printed. As the recursion unwinds, it comes back to the lastmost call. The lastmost call was 7. It says, okay, print 7, and now print 7's right subtree. Well, again, that's an empty one, so nothing gets printed there. It'll come back and then do the same thing with 15. I've done everything to the left of 15. Let's print 15 and its right. And doing that kind of all the way throughout the tree means that we'll get the numbers out in sorted order. Right, 5, 17, 7, 15, 32, 57, 59, 62, 71, 79, 93. So it does an in-order traversal on a binary search tree, right? Rediscovers, visits all the nodes from smallest to largest. Question? So duplicates, you just have to have a strategy. So it turns out in the map, the duplicates overwrite. So anytime you get a new value, you put it there. Typically, right, you just need to decide, do they go to the left or do they go to the right? So that you know when you're equal to, if you wanted to find another one of this, where would it go? In a lot of situations, you just don't have duplicates, so it's not actually a big deal. But if you can't throw them arbitrarily either side, because then you would end up having to search both sides to find them, right? So you want to just know that it's less than or equal to on the left and greater than on the right. And so in order, that's pretty neat, right? That means, for example, if for purposes of being able to iterate over something, you were to walk the structure in order, then you can produce them back out in sorted order, which tends to be a convenient way to print the output. There's a lot of situations where you do want that browsable list in alphabetical or numerical order, and the tree makes that easy to do. When it comes time to delete the tree, I'm going to need to go through and delete each of those nodes individually, the same way I would on a linked list, right, to delete the whole structure. The order of traversal that's going to be most convenient for doing that is to do it post-order, which is to say when I'm looking at the root node 57, I want to delete my entire left subtree recursively, delete my entire right subtree recursively, and only after both of those pieces have been cleaned up, delete the node we're on. So deleting down below to the left, down below to the right, and then delete this one. If I did it in the other order, if I tried to delete in between in the in order or in the pre-order case where I did my node and then recurred to my subtrees, right, I'd be reaching into parts of my memory I've deleted. So we do want to do it in that order. Okay. So recursion, coming back to visit you again. Let's talk about how to make map work as a tree. So you can think about what maps hold. Maps hold a key, which is string type, a value, which is client, elem type, value type, some sort of template parameter there. We're now going to build a structure that wraps those two things with a pair and adds to it, right, these two additional pointers to the left and the right subtrees that point back to a recursive struct, just like the one we had. The one data member that the map will have at the top is just that root pointer, the pointer to the node at the top of the tree. And then from there, we'll traverse pointers to find our way down to other ones. And we will organize that tree for the binary search property. So using the key as the discriminant, right, of what goes left and right, will be compare each new key to the key at the root and decide, is it going to go in the left subtree root or the right subtree, and so on down to the matching position when we're doing a find, or to find the place to insert if we're ready to put a new node in. So get value and add will both have very similar structures, right, in terms of searching that tree from the root down to the leaf to find that match along the way, or to report where to put a new one in. So let's look at the actual code. I have my struct, has the string key, has the value type node, 2 pointers there, and then the one data member for the map itself here is the pointer to the root node. I also put a couple of helper member functions that I'm going to need. That the searching the tree and entering a new node in the tree are going to require a little helper, and we're going to see why that is. That basically the add and get value public member functions are just going to be wrappers that turn around and pass the code off to these recursive helpers. And in these cases, right, the additional information that each of these is tracking is what node we're at as we work our way down the tree. That the initial call to add is just going to say, well, here's a key and a value, go put it in the right place. And that while we're doing the recursion, we're going to need to know where we are in the tree. And so we're adding that extra parameter in the way that a lot of recursive code needs. Is just a little more housekeeping, and that housekeeping is what part of the tree we're currently searching or trying to enter into. Okay. So this is the outer call for get value. So get value is really just a wrapper. It's going to call tree search. It's going to pass the starting value for root as the beginning point for the search, looking for a particular key. And then what tree search is going to return is a pointer to a node. If that node was not found, if there was no node that has a string key that matches the one that we're looking for, then we'll return null. Otherwise, we'll return the node. And so it either will error when it didn't find it or pull out the value that was out of that node structure. So this part looks pretty okay. The template, right, is always just a little bit of goo up there, right, seeing kind of the template header on the top and the use of the val type and all this other stuff. It's going to get a little bit worse here, so just kind of hopefully take a deep breath and say, okay, that part actually doesn't scare me too much. We're going to look at what happens when I write the tree search code, where it actually really goes off and does the search down the tree, and there's going to be a little bit more machinations required on this. So let's talk about it first, just what the code does, and I'm going to come back and talk about some of the syntax that's required to make this work correctly. So the idea of tree search is given a pointer to a particular subtree, could be the root of the original tree or some smaller subtree further down, and a key that we're looking for, we're going to return a match whenever we find that node. So looking at the step here, whereas if the key we have matches the key of the node we're looking at, then this is the node. This is the one we wanted. Otherwise, right, we look at two cases. If the key is less than this node's key, then we're going to just return the result from searching in the left subtree. Otherwise, it must be greater than, and we're going to search into the right subtree. So in this case, right, duplicates aren't allowed, so actually there will be exactly one match if at all. And when we find it, we return it. The other case that needs to be handled as part of our base cases is what if we ever get to an empty tree? So we're looking for 32, and the last node we just passed was 35. We needed to be to the left of it, and it turns out there was nothing down there. We have an empty tree. We'll hit this case where t is null, and we'll return null. That means there was never a match to that. There's no other place in the tree where that 32 could have been. The binary search properly completely dictates the sequence of left and right turns, so there's nowhere else to look. So that's actually really solving a lot of our, cleaning up our workforce, streamlining where we need to go, because the tree is organized exactly to kind of bop through the midpoint and then the quarter point and then the eighth point to narrow down on where we could go. So as it is, this code works correctly. So if you have any questions about kind of how it's thinking about doing its work, and then I'm going to show you why the syntax is a little bit wrong, though. Okay, so let's talk about this return type coming out of the function. So let's go back to this for a second. That node is defined as a private member of the map class. So node is actually not a global type. It does not exist outside of the map class. Its real name is map val type colon node. That's its full name, right? Is that. Now, inside the implementation of map, which is to say inside the class map or inside member functions that we're defining later, you'll note that we can just drop that, the big full name, the kind of, my name is Mr. such and such and such and such. It's like, okay, you can just call it node, the short name, internal to the class, because it's inside that scope, and it's able to say, okay, in this scope, is there something called node? Oh, there is. Okay, that's the one. Outside of that scope, though, if you were trying to use this outside of the class somewhere or some other places, right, it's going to have a little bit more trouble with this idea of node by itself. It's going to need to see that full name. So let me show you on this piece of code that node here, right, happens to be, in a slight quirk of the way C++ define things, that use of node is not considered in-class scope yet. That the compiler leads from left to right. So we'll look at the first one. It says template type name val type. And so what the compiler's seen so far is it says, I'm about to see something that's templated on val type. So it's a pattern for which val type is a placeholder in. And then it sees val type as the return value. And it says, okay, that's the placeholder. And then it sees this map angle bracket val type colon. And it says, oh, okay, this is within the thing that I'm defining here is within scope of the map class. And so it sees the map templated on val type colon. And then as soon as it crosses those double colons, from that point forward, it's inside the map scope. And so when I use things like tree search or I use the name node, it knows what I'm talking about because it says, oh, there's a tree search in map class. There's a node struct in map class. It's all good. In the case of this one, I've seen template type name val type. And at this point, right, it doesn't know anything yet. And so it sees me using node, and it says, node? I've never heard of node, right? I'm in the middle of making some template based on val type, but I haven't heard anything about node. Node isn't something that exists in the global namespace. You must have made some tragic error. What it wants you to say is to give it the full name of map angle bracket value type : node. That the real full, this is my name, and I otherwise, right, it will be quite confused. If that weren't enough, you'd like to think that we were done with placating the C++ compiler, but it turns out there's one other little thing that needs to happen here, which is there is an obscure reason why, even though I've given it the full name, and I feel like I've done my duty in describing this thing, that the compiler still is a little bit confused by this usage. And because the C++ language is actually just immensely complicated, and there's a lot of funny interactions, there are a couple situations it can get into where because it's trying very hard to just read left to right and see the things, that sometimes it needs to know something in advance that it doesn't have all the information for. And it turns out in this case there's actually some obscure situation where it might not realize this is really a type. It might think it was more of a global constant. That we actually have to use the type name keyword again here. On this one construction that is basically a hint to the compiler that says the next thing coming up really is a type name. So given that you can't tell that, you'd think it would be obvious. In this case, it doesn't seem like there's a lot for it to be confused at, but there's actually some other constructions that we can't rule out. And so the compiler is a little bit confused in this situation, and it wants you to tell it in advance. And so I'll tell you that the basic rules for when you're going to need to use this is exactly in this and only this situation. And I'll tell you what the things are that are required for type name to become part of your repertoire. You have a return type on a member function that is defined as part of a class that is a template, and that type that you are using is defined within the scope of that template. So it's trying to use something that's inside a template class scope outside of that scope that requires this type name. And the only place where we see things used out of their scope is on the return value. So this is kind of the one configuration that causes you to have to do this. It's really just, a little bit of a C++ quirk, right? It doesn't really change anything about what the code's doing or anything interesting about binary search trees, but it will come up in any situation where you have this helper member function that wants to return something that's templated. You have to placate the compiler there. The error message when you don't do it actually turns out to be very good in GCC and very terrible in Visual Studio. GCC says type name required here, and Visual Studio says something completely mystical. So it is something just to be a little bit careful about trying to write that kind of code. Question?
The asterisk?
So the asterisk is just because it returns a pointer, right? That's in all of the situations, right? I'm always returning a pointer to the node back there. So I can say, here's the pointer to the match I found, or null when I didn't find one. All right. That's a little bit of grimy code. Let's keep going. So how is it that add works? Well, it starts like get value. That the strategy we're going to use for inserting into the tree is the really simple one that says, well, don't rearrange anything that's there. So, for example, if I were trying to put in the number 54 into this tree, you could say, well, you could imagine putting it at the root, moving these things around, doing all that stuff. Imagine that your goal is to put it in with the minimal amount of rearrangement. So leaving all the existing nodes connected the way they are, we're going to follow the binary search path of the get value code to find the place where 54 would have been, right, if we left everything else intact. So looking at 57, you could say, well, it has to be to the left of 57. Looking to the 32, you say, well, it has to be to the right of the 32. Here's where I get to an empty tree, then we say, well, that's the place we'll put it. We're going to tack it off, kind of hang it off one of the leaf nodes, or not necessarily leaf, but one of the empty trees along the frontier, the bottom of that tree. And so we'll just walk our way down to where we would fall off the tree and then put the new node in place there. So if I want to put the node 58 in, I'll say it has to go to the right, it has to go to the left, it has to go to the left, it has to go to the left, it'll go right down there. If I want to put the node 100 in, it has to go right, 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 right. That just kind of following the path, leaving all the current pointers and nodes in place, kind of finding a new place, and there's exactly one, right? That given any number and a current configuration, and the goal of not rearranging anything, there's exactly one place to put that new node in there that will keep the binary search property intact. So it actually does a lot of the decision making for us, right? We don't have to make any hard decisions about where to go. It's just all this left, right based on less than and greater than.
What if the values are equal?
So the values are equal. You have to have a plan, right? And it could be that you're using all the less, less is less than or equal to or greater than or equal to. You just have to have a plan. In terms of our map, it turns out equal to overwrites. So we handle it differently, which is we don't ever put a duplicate into the tree. So the add call is basically going to just be a wrapper that calls tree enter, starting from the root with the key and the value, that then goes and does the work, right, to go walk its way down to the bottom and find the right place to stick the new one in. All right. Here is a very dense little piece of code that will put a new node into a tree using the strategy we just talked about of don't rearrange any of the pointers, just walk your way down to where you find an empty tree and then replace that empty tree with a singleton node with the new key and value that you have. So let's not look at the base case first. Let's actually look at the recursive cases, because I think they're a little bit easier to think about. Is if we ever find a match, so we have a key coming in and it matches the current node, then we just overwrite. So that's the way the map handles insertion of a duplicate value. In some other situation, you might actually insert one, but in our case, it turns out we never want a duplicate. We always want to take the existing value and replace it with a new one. So if it matches, we're done. Otherwise, we decide whether we need to go left or right. Based on the key we are attempting to insert and the current node's value, it either will go in the left of the subtree, left or the right, and in which case we make exactly one recursive call, right, either to the left or the right, depending on the relationship of key to the current key's value. And then the one base case that everything eventually gets down to that's going to create a new node is when you have an empty tree, then that says that you have followed a path that has led off the tree and kind of fallen off the bottom. It says replace that with this new singleton node. So we make a new node out in the heap. We're assigning the key based on this, assigning the value based on the parameter coming in, and then we set its left and right's null to do a new leaf node, right, has left and right null subtrees. And the way this got wired into the tree, right, you don't see, well, who is it who's now pointing to this tree? This new singleton node that I placed into here, that you don't really see typically that wire coming into it, who is pointing to it, is actually being done by virtue of T being passed by reference. That the node right above it, right, the left or the right of what's going to become that node's parent of the new node being entered was passed by reference. It previously was null, and it got reassigned to point to this new node. So the kind of wiring in of that node is happening through the pass by reference of the pointer, which is a very tricky thing to kind of watch and get your head around. Let's look at the code kind of operating. You have a question?
Yes.
Yeah.
Previous slide, I was wondering if key equals T arrow key. Do you explain that little step?
So this step is just saying, if in the case of the map, right, if we ever find an existing entry that has that key, we overwrite. So in the map, if you've said previously, Bob's phone number is this, and then you install a new phone number on Bob, if it finds a match to Bob saying Bob was previously entered, it just replaces his value. So no nudes are created, no pointers are rearranged. It commandeers that node and changes its value. That's the behavior specified by map. So if we have this right now, we've got some handful of fruits, right, that are installed in our tree with some value. It doesn't matter what the value is, so I didn't even bother to fill it in to confuse you. And so this is what I have. Papaya is my root node, and then the next level down has banana and peach, and then apple, melon, pear, whatnot. So root is pointing to papaya right now. When I make my call to insert a new value, let's say that the one I want to put in the tree now is orange, the very first call to tree enter looks like this. T is the reference parameter that's coming in, and it refers to root. So the very first call to tree enter says, okay, please insert orange and its value into the tree who is pointed to by root. Okay, so it actually has that by reference. It's going to need that by reference because it's actually planning on updating that when it finally installs the new node. So the first call to tree enter says, okay, well, is orange less than or greater than papaya? Okay, orange precedes papaya in the alphabet. So it says, okay, well then call tree enter this second time passing the left subtree of the current value of t. And so t was pointing to, it was a reference to root right then. Now t becomes a reference to the left subtree coming out of papaya. It says, okay, now for the tree that we're talking about here, which is the one that points to the banana and below, right? That's the new root of that subtree is banana. It says, well, does orange go to the left or the right of the root node banana? And it goes to the right. So the third stack frame, right, of tree enter now says, well, the reference pointer is now looking at the right subtree coming out of banana. And it says, well, does melon go to the left or the right of that? It goes to the right. And so now on this call, right, the current value of t is going to be null. It is the reference, right, so a synonym for what was the right field coming out of the melon node. And this is the case where it says, okay, well, if orange was in the tree, then this is where it would be hanging off of. It would be coming off of as the right subtree of melon. That part is null, and so that's our place. That's the place where we're going to take out the existing null, wipe over it, and put in a new pointer to the node orange that's out here. And so that's how the thing got wired in. It's actually kind of subtle to see how that happened, right? Because you don't ever see somewhere a direct assignment like t's left equals this, right, equals that new node, or t's right equals that new node, that it happened by virtue of passing t right by reference, t left by reference into the calls further down the stack, that eventually, right, when it hit the vase case, it took what was previously a pointer to null and overrode it with a pointer to this new cell that then got attached into the tree. Take a look at this piece of code. That by reference there turns out to be really, really important, right? If that t was just being passed as an ordinary node star, nodes would just get lost, dropped on the floor like crazy, right? For example, consider the very first time when you're passing in root and root is empty. If root is null, it would say, well, if root is null, and then it would change this local parameter t equals some new node of these things, right? But if it wasn't really making permanent changes to the root, it wasn't really making root point to that new node, root would continue pointing to null, right? And that node would just get orphaned. And every subsequent one, the same thing would happen. So in order to have this be a persistent change, right, the pointer that's coming in, you know, either the root in the first case or in the t left or t right in subsequent calls, right, needed to have the ability to be permanently modified when we attach that new subtree. That's really very tricky code, you know. So I would be happy to try to answer it, or questions, or kind of go through something to kind of get your head around how it's doing what it's supposed to be doing there. If you could ask a question, I could help you, or you could just nod your head and say, "I'm just totally fine."
Could you have used the tree search algorithm that you programmed before?
You know, they're very close, right? And where did I put it? Oh, it's on this slide. That the problem with this one right now is it does really stop and return the null. So I could actually unify them, but it would take a little bit more work. And at some point, right, there's a point where you say, wow, I could unify this at the expense of making this other piece of code a little more complicated. So in this case, I chose to keep them separate. It's not impossible to unify them, but you end up having to point to where the node is, or a null where you would insert a new node, which tree search doesn't care about, but tree enter does. So it actually would kind of modify it to fit the needs of both at the expense of making it a little more awkward on both sides. Question here.
Yeah, can we go back to the picture of the tree where you're inserting the number?
Or
the number example?
Yeah, sure.
If you were inserting 54, where you said, wouldn't, if we call the print, wouldn't it print out of order?
So 54 would go left of 57, right of 32, so it'd go over here, right? But the way in-order traversals work, right, is it kind of says, it's a print everything in my left subtree, print everything in my left subtree. So it kind of prints 7, and as it came back, 5, 32, and then it would print 54 before it got to the 57. So an in-order traversal of a binary search tree, as long as the binary search tree property is correctly maintained across it, will print them in sorted order. It's almost like, don't even think too hard about it. If everything in my left subtree is smaller and everything in my right subtree is greater than me, that if I print all of those and myself and then print those everywhere, I have to come out in sorted order, right? If the property is correctly maintained in the tree, then that, by definition, right, is a sorted way to pass through all the numbers. But if at any point, right, an in-order traversal was hitting numbers out of order, it would mean that the tree wasn't properly organized. So let's talk about how well it works. So then it turns out there's a couple of other operations on the tree, things like doing the size, right, which would count the number of members, which you could do by just doing a traversal, or you might also do by just caching a number that you updated as you added and removed nodes. And then contains key is basically just a tree search, right, that determines whether it found a node or not. That the rest of the implementation is not interesting. There's also deleting, I guess, but I didn't show you that. But the space use. So how does this relate to the other existing known implementations, right, we have for map? Is it adds certainly some space overhead. We're going to have 2 pointers, right, a left and a right off every entry. So every entry is guaranteed to have an excess 8-byte capacity relative to the data being stored. It does actually add nodes, though, tightly to the allocation. So like a linked list, right, it allocates nodes on a per entry basis. So there's actually not a lot of reserve capacity that's kind of waiting around unused the way it might be in a vector situation. And the performance of it is that it's based on the height of the tree. That both the add and the get value are doing a traversal starting from the root and working their way down to the bottom of the tree, either finding what it wanted along the way or falling off the bottom of the tree when it wasn't found or when it needs to be inserting a new node. That height of the tree, you're expecting it to be logarithmic. So if I look at, for example, the values, I've got 7 values here, 2, 8, 14, 15, 18, 20, 21. Those 7, 8 values, right, can be inserted in a tree to get very different results. There's not one binary search tree that represents those values and uniquely, that depending on what order you manage to insert them, you'll have different things. For example, right, given the way we're doing it, whatever node is inserted first will be the root. And we never move the root, right? We leave the root alone. So if you look at this kind of as a historical artifact, you could say, well, they entered a bunch of numbers, and this is the tree I got. Well, I can tell you for sure that 15 was the very first number they entered. There's no other possibility, right? 15 got inserted first. The next number that got inserted was one of 8 or 20. I don't know which. But I can tell you, for example, that 8 got inserted before 14. That in terms of a level-by-level arrangement, the ones on level 1 were always inserted before the ones underneath it on level 2. But one possibility I said here was, well, maybe 15 went in first, and then 8, and then 2, and then 20, and then 21, and then 14, and then 18. There's some other rearrangements that are also possible that would create this exact same tree. And there are other variations, right, that produce a different but still valid binary search tree. So with these 7 nodes, right, this tree is height 3 and is what's considered perfectly balanced, right? Half the nodes are on the left and the right of each tree all the way through it, leading to that just beautifully balanced result we're hoping for, where both of our operations, add and get value, will be logarithmic. So if I have 1,000 nodes inserted, that height tree should be about 10. And so if everything kind of went well and we got an even split kind of all the way around, right, then it would take 10 comparisons to find something in that tree or determine it wasn't there, and also to insert, which was the thing we were having trouble with the vector case, that because that search, right, leads us right to the place where it needs to go, then the inserting, because of the flexibility of the pointer-based structure, is very easy. We can make both that insert and add operate logarithmically. Let's think about some cases that aren't so good. I take those same 7 numbers and I insert them not quite so perfectly, and I get a not quite so even result. So on this side, right, I can tell you 20 was the first one inserted. It was the root, and the root doesn't move. But then the subsequent ones was it inserted an 8, and then a 21, and then an 18, and then a 14, and then a 15, and then it went back and got that 2. The one over there, another possibility for how it got inserted 8, 18, 14, 15, and so on. These are not quite as balanced as the last one, but they're not terribly unbalanced, right? They're like a 1 or 2 more than the perfectly balanced case. So at logarithmic plus a little constant, right, still doesn't look so bad. Okay, how bad can it really get? It can get really bad. So I can take those 7 numbers and I can insert them in the very worst case and produce a completely degenerate tree. Where, for example, if I insert them in sorted order or reverse sorted order, I really have a linked list, right? I don't have a tree at all, right? It goes 2, 18, 14, 15, 18, 20, 21. That's still a valid binary search tree. If you print it in order, it still comes out in sorted order, right? It still can be searched using a binary search strategy. It's just because the way it has been divided up here, right, it's not buying us a lot. So if I'm looking for the number 22, I'll say, well, is it to the left or the right of 2? Oh, it's to the right. Is it the left or right of 8? Oh, it's to the right. Is it the left or right? You know, like all the way down. And so finding 22 meant looking at every single one of the current entries in the tree before I could conclude, as I fell off the bottom, that it wasn't there. Similarly, kind of over there, right? That it didn't buy us a lot. It has a lot to do with how we inserted it as to how good a balance we're going to get. And there are some cases that will produce just drastically unbalanced, right? Things that require linear searches, totally linear, right? To walk that way down to find something. There's a couple of other degenerate trees, just to mention that it's not only the sorted or reverse sorted, there's also these other kind of sawtooth inputs, they're called, where you just happen to, at any given point, have inserted the min or the max of the elements that remain. So it kind of keeps dividing the input into 1 and n minus 1. So having the largest, then the smallest, then the largest, then the smallest, and then subsequent smallest down there can also produce a linear line. It's not quite just all down the left or down the right, but it does mean that there's every single node has an empty left or right subtree is what's considered the degenerate case here, and these both have the same property where, you know, half of the pointers right off the each cell are going nowhere. There's an interesting relationship here, right, between these worst case inputs for tree insertion and quicksort, and they're actually kind of exactly one-to-one. That what made quicksort deteriorate was when the next element of the input, right, was the max or the min of what remained, and that's exactly the same case for tree insertion. Max or min of what remains means that you are not dividing your input into two partitions of kind of roughly equal size. You're dividing them into the 1 and n minus 1, which is getting you nowhere. What do you get to do about it? Well, you have to decide, first of all, if it's a problem worth solving. So that's what the first one says, is sometimes you actually just say, well, it will happen in some inputs that I consider rare enough that it will degenerate. I don't think they're important enough or common enough to make a big deal out of. I don't think that applies here because it turns out getting your data in sorted order is probably not unlikely, that somebody might be refilling a map with data they read from a file that they wrote out in sorted order last time. So saying that, you know, yeah, if it's coming in sorted, I am willing to tolerate that. It's probably not going to work. And there's two main strategies right then if you've agreed to take action about it, about what you're going to do. The first one is sort of is to wait until the problem gets bad enough that then you decide to do something about it. So you don't do any rebalancing as you go. You just let stuff go, left, right, whatever's happening, and you try to keep track of the height of your tree. And you realize when the height of the tree seems sufficiently out of whack with your expected logarithmic height to do something about it, and then you just fix the whole tree. You can clean the whole thing up, pull them all out into a vector, rearrange them, put them back in so that the middlemost node is the root all the way down, and kind of create the perfectly balanced tree, and then keep going and wait for it to get out of whack and fix it again. So kind of sort of wait and see. The other strategy, and this happens to be a more common one done in practice, is you just kind of constantly do a little bit of fixing up all the time. That whenever you notice that the tree is looking just a little bit lopsided, you let it get a little bit, like usually you'll typically let it be out of balance by 1. So you might have height 4 on this side and height 3 on that side. But as soon as it gets to be 3 and 5, you do a little shuffle to bring them back to both 4. It involves just a little bit of work, right, all the time, to where you just don't let the tree turn into a real mess. But there's a little bit of extra kind of fixing up being done all the time. And so there's a particular kind of tree that's discussed in the text which you can read about, but we won't cover as part of our core materials, called the AVL tree, which is just interesting to read about, just to see, okay, what does it take, right? What kind of process is required to kind of monitor this and do something about it. And so if we have that in place, right, I'm going to skip what that says, we can get it to where the binary search tree form of this, right, is logarithmic on both inserting new values and searching for values, right, which is that holy grail of efficiency boundary. You can say, yeah, logarithmic is something we can tolerate by virtue of adding 8 bytes of pointers, potentially some balance factor and some fanciness, right, to really guarantee that performance all over, but gets us somewhere that really will scale very, very well for thousands and millions of entries, right? Logarithmic is still a very, very fast function. So creates a map that actually could really kind of go the distance and scale. So that's your talk about binary search trees. We will come back and talk about hashing and graphs and stuff next. So I will see you on Wednesday.